Okay, so for today's video, we've discussed already about isometric or isochoric process wherein the volume is constant during the process of the ideal gas. So now, let's proceed to the next type of process of ideal gas, which is the isobaric process. Okay, so how are we going to remember what isobaric process is? So just remember isobaric or bar. So barometric pressures or bar pressure. So, dyan papasok ngayon si isobaric process. Okay? So, as you can see here, based on the definition, isobaric process is also known as isopiastic process, wherein the assumption, so our assumption for an isobaric process is pressure is constant. Okay? So, as you can see here, we have also, just like in isometric process, we have a PV and TS curve or diagram. Okay, so as you can see here, isobaric process is represented by a straight horizontal line. Okay, straight horizontal line, and this horizontal line is represented by dV or the change in volume. Okay, as you can see as well, P is constant, so there is nothing changing when it comes to the pressure of the substance. Okay, so let's try to derive some of the equations that is necessary for solving this one. Okay, as you can see that the area bounded by your PV diagram corresponds to your, so PdV, that is your non-flow work. Okay, so let's start first with combined gas law. Okay, so combined gas law is what we know as P1V1 over T1 is equal to P2V2 V2. Okay, so as you can see, the assumption now is the pressure is constant, so therefore we can eliminate pressure from your equation. So we have V1T1 is equal to V2T2. Okay, so by performing separation of variables, all of the V and all of the T, so all at the same side. Okay, so as you can see here, we can have V2 over V1 is equal to T2 over T sub 1. So this is your equation number 1. Okay, next. The next equation is your change in internal energy. So as we've said before in isometric process, that the change in internal energy is always absolute. So regardless of the process, we say that the process here is constant pressure, your internal energy will still be mcv dt or mcv T2 minus T1. Okay, so this is your equation number 2. Next, the change in enthalpy. So as we've said a while ago in isometric process, so so enthalpy is mcp dt. So that is equation number 3. Okay, leading us to the equation of heat, wherein we've said that heat is always dependent on the process, wherein the heat has the general equation of mc dt. And see here, since we are observing a process that has a constant pressure, therefore heat is represented by this equation. This is equation number 4. Okay, as you can see, equation number 4 and equation number 3 are equal to each other. So therefore, we can conclude that isobaric process, the enthalpy is equal to your heat. Okay, so that is our first conclusion. Next, letter E. So for letter E, let's proceed with the non-flow work. So we've said earlier that the non-flow work is the area bounded by your PV diagram. Okay, So we've said in an isobaric process that P is equal to C. Okay? Now, let's substitute C in this equation. We will have from point 1 to point 2, C dV. Okay? So we've said in integral, so if we have a constant inside our integral sign, what we do is that we eliminate it inside our integral sign. We have C integral of dV from point 1 to point 2. Okay? Then, let's assess. So what is the integral of dV from point 1 to point 2? So let's expand that. We will have C multiplied by V2 minus V sub 1. Okay? So this is not yet our final equation because we've said that C is equal to P. So this C right here, let's substitute it by P. So that is P V sub 2 minus V sub 1. Okay? So this is our non-flow equation for letter E. So that is equation number 5. Okay? So for the steady flow work, so once you are asked to locate for the steady flow work of a substance, so the steady flow work is given by the negative integral of V dP. Okay? But we've said that pressure is constant, so therefore there is no rate of change within the pressure, so therefore this term is equal to 0. So 0 times the function V, so regardless of how high the magnitude of it, it will always be 0. So the steady flow work here, when we use negative VdP, is 0. So this is equation number 6. Okay? Next, letter F. So the last thing is your change in enthalpy, entropy. I'm sorry. So this is dq over t from point 1 to point 2. Okay? As you can see, dq, we've said earlier that q is equal to your enthalpy in an isobaric process. Okay? So therefore, let's substitute this equation mCp dt in our entropy equation. So this will be integral of from point 1 to 2 of mCp dt over t. Okay? So since the assumption is the mass is conserved and Cp is constant as well, so we will eliminate it outside the integral. So we will have mCp integral from point 1 to point 2 of your dt over t. So therefore, the change in entropy, the equation for the change in entropy is given by mCp. So this is dt over t or du over u. This is natural logarithm of t2 over t sub 1. Okay? So this is your equation number 7. This is equation number 7. So as much as possible, always be aware with what process you are dealing with, because Cp and Cv is always dependent on the process being the fluid that the fluid is undergoing. So let's say constant volume, constant pressure. So always be aware of the specific heat that you are going to use. Okay? So for the next video, so these are the basic equations that you need to do to be familiarized. And of course, don't forget as well your equation of state, or PV is equal to MRT. Okay? Because that is very powerful in determining the conditions or the states of your substance. Okay? So in the next video, let's try to answer problems with regards to isobaric process or a constant pressure process. So I hope to see you there.